Welcome to the lecture on the homework assignment. This portion of the lecture we're going to discuss the homework, and hopefully you've already completed the homework before this, because then you can get maximum benefit about the lecture. The first question on the homework assignment was to look up jobs on Indeed, and really any response is good. What I want you to do on that question is to try to understand that many IE jobs cover the topics in this course, and the topics in this course are valuable. So we'll skip that question. The second question was, what is the mean absolute deviation of an exponential smoothing forecast and a constant forecast for a given problem? And so let me switch to my laptop so we can all take a look at this. So what I want you guys to do is to take this to Excel, right? And so we have our demand and our actual and a forecast. So let me copy this into Excel. Okay, Excel's opening. He's thinking about pasting it. Okay, it pasted it. Okay. It's thinking about deleting that. Okay. So, how do we do, first of all, the exponential smoothing? Well, in the problem it said our initial forecast was 500 in the first month, correct? So there's the 500. Now for the subsequent months, how do we forecast if our previous forecast was 500 and the actual was 527? So we're doing exponential smoothing. Alpha equals 0.15, right? So we take 0.15 times the previous value times the previous value plus 0.85 times the prior forecast. And we fill that down. Because remember, exponential smoothing, my forecast at time t equals alpha my actual t minus 1 plus 1 minus alpha my forecast t minus 1. Okay? So what I'm basically saying is I'm going to guess my new value is my old forecast, or my old value times alpha plus 1 minus alpha times my forecast. Does everybody get that? So alpha is typically between 0.5 and 0, okay? If alpha is 1, what am I doing? I'm just taking my prior value, right? There's no smoothing of the forecast, so just take prior. Alpha is 0 would mean just take forecast. And that's a constant value. Okay? So alpha between those two extremes, you take the 1. Now, we want to compute MAD, mean absolute deviation, and that's the summation of forecast t minus actual t, the absolute value of that, t equals 1 to n, all over n. Okay? Everybody get that, right? So this is the MAD Expo smoothing. And so we do forecast, the absolute value of forecast minus actual. And the first period we have 27, then 23, then 18, and then 30. Now, a constant forecast of 500, we'll just put 500 and make it constant. And the error, the MAD is taking the average of the individual errors. And what we see is the constant forecast in this case is better. 23 as opposed to 24. So the only trick in this is to just remember that you use 0.15 of your previous actual and 0.85 of your previous forecast. Everybody got that? Can do that on the test, I hope. So, okay. And the constant forecast in this case has a lower error. Discuss the advantages and disadvantages of the subjective forecasting methods discussed in the class. And what were the four methods? They were sales force composition. Ask your sales force, each person estimate a value. What's the advantage of that? Well, your sales force may have a good understanding of their own customer, right? What's the disadvantage?
They're optimistic.
Salespeople are either optimistic or pessimistic, depending on which way they think makes them look better, right? They'll be highly biased towards the idea that if they miss the number, they'll get in trouble, or if they put the number too low, maybe they'll get a better number, or maybe they'll put it high because they're optimistic. But they will be making a political decision as much as they'll be making an actual decision. They will put it very high so that they can allocate that inventory to them. Customer survey was discussed. Well, obviously, if you have a few customers, that will work, but most companies have quite a few customers, and your customers may not actually know what they want, right? Delphi method and jury of expert opinion. Jury of expert opinion, just ask a bunch of experts. They don't re-estimate their forecast. Delphi method is very effective, but it's very time-consuming. I get the experts in a room, ask a question, and then give them feedback about the answer, such as the average value of the forecast, right? And then make them reevaluate in regards to that answer. When should one use a subjective forecasting method instead of a time series-based method, exponential smoothing, moving average, autoregressive moving average, etc.? Well, subjective methods should be used when the prior history provides limited information about the future, such as major events occurring, product launch, competitors, macroeconomic events, recessions, etc. So if you think next year is going to have nothing to do with the previous year, don't use last year's data to forecast, right? You have to have some expert opinion. And those are called change of regime in economics, which makes the past history a poor predictor of the near future. Does that make sense to everybody? The next question is, you're using a part at a constant rate of $5,000 per year. Each bolt costs $2. The inventory costs 25% of the value of the item. The ordering cost for the item is $25. What is the optimal EOQ? Well, the setup cost is $25. The holding cost is 25% of $2 or 50 cents per item year. And the demand is 5,000 units per year. So this is units per year. This is cost per part per year. And this is setup per order. Well, you just simply plug them into the EOQ equation, and you get 707 items. Did everybody get that who did this? I hope so. Now, part B asks, what is the annual setup and holding cost and part cost? Well, the cost of the parts is the price, C, times lambda. So we're demanding 5,000 parts. Each part costs $2. So it's $10,000 per year. Well, how many times am I going to have to set up? How many times am I going to have to order? Well, I'm using 5,000 of them, and I'm ordering 707 at a time, right? So I'm going to have to order about 5,000 divided by 707 times per year, about 7 times per year, right? I multiply by the setup cost, which is $25, right? And that gives me the total cost of setups in a 1-year period. So I'm paying $176 per year to order the item. The holding cost is HQ over 2, and we discussed that early in the semester, right? And so my average inventory level under EOQ is 707 divided by 2. Remember, demand is constant. So my plot of my inventory is a function of time under EOQ. And these are all going to be identical. That's Q. This is time. This is inventory. So what's my average level going to be? Q by 2. What's my average inventory cost? It'll be HQ by 2. Cost per item? And then this is average inventory. Everybody see that, right? So the holding cost is $176. Total cost is $10,352. Okay? Now, if I force you to order 1,000 units, okay? Well, what's the holding and setup cost? Just make Q 1,000, right? And plug it into the equations. And we find that because I forced you to go from 707 to 1,000, obviously the cost went up, right? And so it used to cost, including parts, $10,352, and now it costs a whopping $10,375. In general, and we talked about this in class, even small changes to the EOQ have limited impact on total cost. And we put up a formula. It's in the notes, okay? But in general, if I make you shift the EOQ quantity just a little, not going to affect cost, right? What does that mean in terms of parts? Let's say the EOQ says 521 parts, but a pallet stores 500. How many should you order? 500, because you don't want to do partial pallets. And the same thing with transportation as well. Let's say I get a big discount shipping in particular quantities, full truckload, and my EOQ says order 1.5 trucks. Don't do that. Order 1 truck, right? So, the EOQ is very robust to small changes, and it typically doesn't impact total costs that greatly. And we have some equations that we can plug into and compute. So if I say supplier A, if you order exactly 1,000 units, is going to give you a $25 discount per part. Well, you would now recompute what's the inventory holding and part cost under that option versus the optimal EOQ. Everybody get that? The next problem is a machine setup cost, a finite production EOQ. So your machine costs $300 to set up. The production rate's 20,000 units per year. The demand rate is 5,000 units per year. The cost of inventory is $1 per unit year. What is the optimal batch size? What is the time between production runs? And how long is the machine on? Well, the optimal EOQ with finite production is the holding cost gets changed, right? So the holding cost is equal to the old holding cost, 1 minus lambda over P. And so my new holding cost is 0.75. My optimal order quantity Q is 2,000 when I plug it in. Now, what is the time between production runs? How long is it between production runs? Well, you take Q divided by lambda. So if I'm producing 20,000 items at a time and the demand is 5,000, the time between production runs would be 2/5 of a year. It's obvious, right, when you say it like that. How long is the machine on? Well, I produce 2,000 units and I can produce 20,000 in a year. So the machine's on for 1/10 of a year, just over a month. So basically, I turn on the machine for a month, and then my whole cycle is 2/5 of a year. Okay? So, what you're doing here is you're building inventory. And this is 1/10 of a year. And this is 2/5 of a year. Okay? And so this is 3/10 in this range and 1/10 here. Okay? Everybody get that? And you're just repeating that cycle over and over again. Now, another thing to remember for the test is the basic equation. Right? So if you increase K, what's going to happen to Q? It's going to go up. Now, if I double K, is it going to double? No. It's going to go up by the square root of 2. And you can show that by Q1 over Q2 with K doubled. And this is 2K lambda over H divided by 2K lambda over H square root. Everything cancels except for square root of 2. If Q1 has twice the setup cost, right? So, obviously, setup cost goes up, order quantity goes up. Demand goes up, order quantity goes up. Holding costs go up, order quantity goes down. And it's related by a factor of the square root. I'm working at a bakery selling cakes. The expected number of cakes per day is given in the table. Well, this is a Newsvendor problem, and you have to compute the underage cost and the overage cost. Well, cakes cost $5 to produce, or no, they're sold for $6. They cost $1 to produce. There is no salvage cost. So the cost of going under is 6 minus 1, or $5. Okay? I missed out on $5 of profit. Cost of going over is $1. I have my $1 of cost. And I can compute the critical ratio of 0.833, go up and find that in the distribution, and it's right there between 4 and 5, and then conclude I should produce 5 cakes. Because you round up the critical ratio. Now, if I was in a situation where I'm using the Newsvendor to compute these cakes, right? Every day, I have to decide how many cakes to make. And I assume it follows that distribution. There's such probability of 1, 2, 3, and 4. Well, what questions would you ask to get it implemented in a real environment? Well, the first one is, does the demand have a different pattern on each day? If so, the optimal order quantity would have to change. Maybe people like to buy cakes on Friday for the weekend, right? So that's the first thing. Second question you have to ask yourself is a little deeper. How can we get the demand stable? Because it's going to work a lot better if my demand's stable and doesn't have such wide variability, right? Because I won't be over and under all the time, I'll be more stable. It's a business question, but can we change the distribution? Can we increase it? And then finally, can we do some sort of just-in-time or store the cakes? Can we store the cake material and partially assembled and then assembled to order? Okay? And all of this on EOQ comes down to, can we reduce variability? Or not EOQ, but Newsvendor. Can we reduce variability? Can we lengthen the time period that items are good for? Those sort of questions. Now I ask you, a manufacturer produces items at a constant rate of 100 per month. The firm has holding cost and setup cost. What model would you consider? So we're talking an assembly line support with holding and setup cost. What model best defines that? EOQ, Newsvendor, QR, big S little s. EOQ. And I would agree with that. That was the answer I put down. But what questions do you have to ask yourself before implementing an EOQ system? What's the big assumption? Demand is constant. What's the next big assumption? Does the lead time have variability? Right? Because if either one of those are violated, you shouldn't be entering EOQ. Because if the lead time has any variability, it's the same. It accomplishes the same thing as the demand not being constant. And you have to do QR because you're going to have variable demand during the lead time. Not due to the demand itself, but due to the lead time. Does it make sense to everybody? Also, if you're implementing such a system, one of the obvious questions I'd ask is, can we get rid of the setup cost? Or why do they originate? And then finally, what impact on transportation cost is going to have on the order quantity? Okay? Because generally, transportation costs go down as you order more and more stuff, right? Till you reach full truck or full rail car. So the next question is, a retail firm is ordering items for summer. What inventory policy most closely matches that we discussed about? Newsvendor, right? Now, what questions would you have to ask yourself before implementing this Newsvendor in a real situation?
Setup costs.
Well, there could be setup costs, I'll grant that. Another question along the same lines is, what is the lead time for this item? The lead time's 6 months. Well, obviously it's a Newsvendor. If the lead time's 2 days, it's not really a Newsvendor, right? Because that's why you said Newsvendor. You assumed what? The lead time for the item was long compared to the length of the summer, which is usually pretty reasonable if you're getting fashion from large suppliers a long ways away. The other question you have to really think about is, what's the cost of going under and what's the cost of going over? That's almost impossible, right? Especially on a fashion item. Because you have to know, well, if you go under, what's going to happen? Well, the customer's not going to have that particular model in stock. But does that mean they don't buy something else from you and equally happy? Like if they didn't know it was on the shelf, would they miss it? Maybe. Does that make sense to everybody? Especially if you got 50 different types of shorts. If one stocks out, it's not a big deal. Now, at the same time, if you stock out and the customer really wanted that particular item, you have to include the cost of goodwill. So while the problem is incredibly easy, it's getting those costs is where you're going to have the problem. And then I ask, how could you forecast the demand for fashion item? Swims, bathing suits, or shorts or shirts for summer?
Moving average.
Okay, you could use a moving average. You could use a historic data. But would you do it for? Let's think of it a different way. You have different factors. Like you could do it for everyone and say, I want to order 10,000 of these per store. But what do you really need? You need the individual item. So what composes an item in fashion? You have style, right? Maybe color, as well as size. Okay? So you have to, if I guess that I need 500 of this style, then I'm going to have to then forecast what? How many in each size category am I going to need? And that gets tricky, right? Because what's the absolute worst thing that can happen? Customer goes into the store and they don't have their size. They have the one size bigger and the one size smaller. That gets really frustrating for the customer. I would almost prefer they go in and they don't see any of them. Make sense?
Yeah.
So you need to really look at your raw data and do what you suggested. Look at last year's data, get an estimate, adjust the estimate according to the market. Now, I would also include a subject matter expert to aid the forecast. Somebody who knows something about fashion. I don't know anything about fashion. I can do the moving average thing. I can do exponential smoothing. I can even do time series method. But you want an expert who could say, well, this year people are not wearing red, or not wearing green, or want yellow. Okay? And then you can adjust your forecast according to the expert, what the data is telling you, macro effects, and, the question of how many to order is really easy if you have an accurate forecast, the undercost and the overcost. Solving the Newsvendor is trivial. It's figuring out all the things around the Newsvendor is where the trouble is. Make sense to everybody? Okay, what is the main difference between EOQ and QR?
EOQ reduces the cost of ordering as well as the holding cost, but the QR is only reducing...
The QR has setup and holding costs. They both have setup and holding.
It just minimizes the holding inventory cost.
QR?
Yeah.
QR has a random demand.
QR has random demand, right? So the only difference between EOQ and QR is random demand or random lead time. As a result, QR has to have an additional cost for stocking out because you can't guarantee with constant demand that you reach zero, right? So QR is holding, setup, and stock out, okay? And the policy is whenever you hit the reorder level, you order up to Q. Higher the reorder point, the less risk of stocking out. Make sense to everybody? So QR is basically the extension of the EOQ, just with a cost for stocking out because of some randomness during the lead time. Okay, any other questions that might help on the homework or the test? We'll have one more review next time where we'll talk about the Procter & Gamble paper and give some examples for the graduate students on some more graduate student level questions, okay? Any further questions? Have a good night, and undergraduates, make sure to organize all your notes and your homework since it is open book, open note.